This is the second part to our stoichiometry series. In the first video, we focused on mass to mass stoichiometry. In other words, we start with the mass of one substance and convert to the mass of another substance. In this video, we are going to volumes. In other words, we'll be dealing with two gases. Sometimes it's easier to measure the volume of a gas than it is to measure its mass. So today's lesson is about volume to volume stoichiometry problems. If you have a volume to volume problem, then you start at the balloon in this diagram, and in order to convert from one substance to another, just like with mass to mass, you have to go through moles. So we will convert from the volume of a given gas by multiplying by the conversion factor 1 mole over 22.4 liters, which is the molar volume of gases. Once you get the first gas changed into moles, you can do a mole exchange based on the ratio from the balanced chemical equation, then convert back to volume of the second gas by doing the reverse conversion factor. Now, 1 mole of any gas at standard temperature and pressure has a volume of about 22.4 liters. It's not exactly 22.4 for every gas, but it's pretty close, and for our purposes, we are going to call that the molar volume of a gas. Each element or compound has its own individual molar mass, but all gases at STP have approximately the same volume. So, when dealing with problems that involve two gases, we can take advantage of this special property of gases and actually make our calculation a little bit simpler than a mass-to-mass problem. What we'll do is I'll give you an example here, and we will work it out in the steps that we did for a mass-to-mass problem and show you what the answer is, and then I'll show you a simplified method that also works. For example, at STP, standard temperature and pressure, how much oxygen is required to react with 5 liters of hydrogen in order to create water according to this balanced chemical equation? Just like with a mass-to-mass stoichiometry problem, once you have a balanced chemical equation, the best thing to do is to write right next to that equation what you're given and what you want to find. We are given 5 liters of hydrogen, and we want to find how many liters of oxygen is required in order to react with that hydrogen. We are not asked to find the amount of water, and so once the equation is balanced, we really don't need that anymore. I recommend marking through it so you don't focus on it. If we do this like a mass-to-mass problem, then what we need is a series of fractions multiplied by each other. We can shorten it up and put it in this grid form. You put what you are given in the first box here, 5 liters of hydrogen. You put what you want to find at the end, liters of oxygen, and then you put a series of conversion factors. So if you follow the mole roadmap, you would see the first conversion is to convert from liters of hydrogen to moles of hydrogen. Now to do that, it says that we need to multiply by 1 mole over 22.4 liters. We have to supply the specific information for this particular problem from this generic conversion factor. So what you would write is 1 mole of hydrogen and 22.4 liters of hydrogen. We can see that the liters in the numerator and the liters in the denominator of hydrogen will eventually cancel each other out once we start multiplying, so we might as well do that now. That way we can see where we are in the problem. Right now we have moles of hydrogen. That is not what we want to find. We want to find liters of oxygen, so we need to keep going. Now what we just did with this conversion is convert to moles of hydrogen, And once you have moles, you can exchange those moles for other moles if you have a balanced chemical equation. In other words, I see in the balanced chemical equation that for every 2 moles of hydrogen, I require 1 mole of oxygen. It's a 1 to 2 ratio. Now my moles of hydrogen are going to cancel. I'm left with moles of oxygen. I need liters of oxygen, so I need to do one more conversion. I go back up to volume by multiplying by 22.4 liters, the molar volume, over 1 mole. I supply the specific information. In this case, the substance is oxygen. The mole of oxygen on top and bottom of this fraction are going to cancel each other. And so what you're left with is 5 times 22.4 liters of oxygen over 22.4. The 22 over 2. The 22.4 are going to cancel out. And so all you're left with is a 5 over 2 liters of oxygen, which of course is 2.5. 5 divided by 2 is 2.5. So we solved that problem using the stoichiometry method that we use for a mass-to-mass problem. It will work. It'll work every time. However, you should note that the first conversion, 1 mole over 22.4 liters, is the reverse of the last conversion, 22.4 liters over 1 mole. That will always be true if you have 2 gases at STP, standard temperature and pressure. Since those two will always cancel each other out as far as the units go, then there's really no need to do a 4-column problem like this. We can reduce it down instead to the given coefficient and the mole ratio. So we can shorten a problem up if it is gas to gas or volume to volume at standard temperature and pressure by using simply a coefficient ratio. Take your volume given, multiply by the coefficient of the unknown from the balanced chemical equation, divided by the coefficient of the given in the balanced chemical equation, and that will give you the volume of the unknown substance that you were asked to find. In other words, it's the coefficients of gases in the balanced chemical equations that shows the volume ratio relationship between 2 gases if they're both at standard temperature and pressure. This ratio mirrors or reflects the same molecular or molar ratio given in the balanced chemical equation. So here's a very similar problem. We will just change the amount. What if we had 35 liters of hydrogen gas? How much oxygen would it require to react? Write what you're given above the hydrogen, 35 liters. Write what you want to find, liters of oxygen. Mark out the water because that is not asked for in the final answer. And all we need to do is multiply that coefficient ratio times the volume given, and we should get the answer. So if you remember from last time, we started with 5 liters, we ended up with 2.5. If we start with 35 this time, we should end up with half of that. So let's see. The volume of the unknown gas, which is oxygen, equals the volume given, which is 35 liters, times the coefficient of the unknown, which is 1, over the coefficient given, which is 2. The hydrogen is the given substance, and so we put the 2 in the denominator. There is no 1 coefficient written down in the way that I've written it on the screen, so if I put a 1 there, I can now see it goes as the numerator of my fraction. 35 liters times 1/2 equals 17.5 liters. This particular case, that means volume of oxygen. Again, this little trick will work every time as long as you are doing a volume-to-volume problem. You have to identify what sort of problem you're working out first. And it only works when the 2 gases are at standard temperature and pressure. Let's look at another example. Calculate how much oxygen is required to burn 4 liters of natural gas. Now, natural gas's formula, or methane, is CH4. If it reacts with oxygen, that means plus O2, and the products of this combustion reaction should be carbon dioxide and water. So here's the balanced chemical equation for the combustion of methane, or natural gas. We are asked to find oxygen, and we're given methane. We do not need the carbon dioxide and the water. Let's list what we're given, 4 liters of natural gas. Let's list what we want to find, liters of oxygen. Let's mark out the rest so we don't focus on those things. Let's take the volume given, which was 4 liters, and multiply by the coefficient ratio. We'll put the coefficient of the unknown, which is oxygen, on top. In this case, the coefficient of the unknown is 2. The coefficient of the given substance, natural gas, is implied to be 1. So it's 4 liters times 2 over 1, which equals 8 liters. It requires 8 liters of oxygen to completely combust 4 liters of methane, natural gas. So this method is pretty simple. You just have to make sure that you're dealing with volume-to-volume problems. I want you to practice this. If you got the worksheet, then you can do that. If not, I'm sure there's some problems on the internet that you could look up. Assuming you did get the worksheet that goes with this unit, then please note there's only 4 problems, but for the first and the third problem, you must balance the equation on your own. You have to have a balanced equation before doing a stoichiometry calculation. Problems 2 and 4 are already balanced. You can just proceed with them. But problem 4 is a little bit different. I was just trying to show you there that we usually measure volume in liters, but you can actually measure it in other units, such as milliliters. So you can actually give your answer in milliliters if you want. So the next slide is the set of problems. And I'll just leave you to it. Please practice your stoichiometry problems.